Everybody. Thank you so much for being here today. I know yesterday was the party, so you guys woke up early. I really appreciate that. Thank you to the organizers. I think that we all can agree that the first day was absolutely amazing and there were just absolutely great talks. My name is Ridhwana. I live in Cape Town, South Africa. These are my favorite photos in case I can convince you to come visit. We have beautiful beaches, great food, colorful communities, incredible safaris, and my absolute favorite is the diverse and friendly people. I'm a lead engineer at Circle, where I work on a large, evolving Ruby system. I'm also a technical writer for the Rails Foundation, where I work on the official Ruby on Rails guides. A big part of both these roles is understanding code that I didn't write. Code that works, but like with any large system, code that takes a little bit of time to understand and reason about. And that brings me to something that happens more times than I'd like to admit. I open a code base, everything works, the tests are green, the system is live. And yet, I feel strangely unsure. Not because I don't know the language, not because the code is unreadable, but because I don't quite know where things live, why certain decisions were made, or what would break if I changed something. That feeling of being able to read code, but not yet understand the system, is what this talk is about. Understanding a code base isn't just a technical one, it's a cognitive one. We're constantly building mental models of how behavior flows, where state lives, what's stable, what's fragile, and which assumptions are safe to make. When those models are wrong or incomplete, even the smallest of changes feel risky. This talk is about that process, not mastering every single detail, but building enough clarity to move forward with confidence and leaving systems better understood than we found them. So I've been thinking about this a lot, and the analogy that comes to me is cooking. I've been cooking for a long time now, not professionally, just consistently over the last few years. My husband has started cooking more recently. He follows recipes closely, he watches YouTube videos, and most of the time, his food turns out pretty great. Shh, don't tell him I said so. But every now and then, something goes wrong. A sauce doesn't thicken, a dough doesn't form, and at that point, the recipe stops helping. And that's, of course, when he calls me into the kitchen. Not because I know the recipe better, but because I've seen these patterns before and I've experienced them in the past. And so I know which variables can move, which ones can't. I don't need a new recipe. I tend to use my existing mental model. And that analogy has felt really close to how I experience complex systems. So what I want to talk about today isn't about how to avoid complexity, but rather how to understand complex systems. Because I don't think avoiding complexity completely is totally realistic. It's how we find footing once our systems grow beyond what we can comfortably hold in our heads. Over time, I've learned that the fastest way to understand a system isn't to read more files, but it's about being deliberate about how you explore the code base, when to zoom in, when to zoom out, how to recognize patterns, and how to understand context, and finally, how to preserve the context that you've learned so that it compounds. When you start exploring a code base for the first time, the instinct is often to zoom out, to get a lay of the land and understand the entire system. I've learned to resist that urge, because in a non-trivial code base, that can be pretty counterproductive. Trying to understand everything upfront almost guarantees that you'll stall. There's too much surface area, too many paths you could follow, and probably not enough signals initially that will tell you which ones matter. Instead, I do the opposite. I zoom in. That's not just how I approach unfamiliar systems, it's also how I onboard people too. Recently, for my team, I onboarded a new front-end engineer. And when a new team member joins my team, I often give them a small bug or a small feature or something that feels off to work on. Not because it's the most important part of the system, but rather it gives them a foundation to start working from. From there, the goal isn't to solve everything at once. It's to answer a series of small questions where each answer unlocks the next question until you have a solid understanding of a narrowly scoped area of the code base. By starting small and staying scoped, you're much less likely to chase dead ends. So practically, my first step is to write down a short list of questions, not architectural questions, but practical ones. For example, at Circle, where I'm the lead engineer of the Email Hub team, we spend a lot of time deliberating about how emails are sent. If I'm trying to understand what happens when someone clicks on a send later button at the top of a screen after configuring an email broadcast, my checklist might include questions like, what record changes when the send later button is clicked? Is the scheduling decision made synchronously or does it happen later in the background job? What would have to fail for this email not to be sent at the correct time? And which part of the system is responsible for triggering the delivery? I'm not answering all of these questions at once because that can be really overwhelming. Instead, I'm picking one question and answering it until I either understand it or I hit a boundary. When behavior crosses boundaries, I reach for flow diagrams. At that point, holding the flow in my head stops working. A quick sketch with boxes and arrow, like the image on the left, helps me to externalize causality and time. What happens synchronously, what happens later, and what happens where the system branches. These diagrams are thinking tools. Once the flow is visible, patterns and assumptions start to surface naturally. It becomes legible to you, your teammates, and increasingly to AI as well. Once I have a hypothesis, I use my editor less as a place to read code and more as a navigation tool. I follow references and call sites to see where methods are actually used, because in Ruby, intent often lives at those call sites. When metaprogramming breaks static references, I use data and follow names instead, searching for strings, callbacks, or dynamic methods like send and define method. And when I need certainty, I add a breakpoint to see how often something runs. At this stage, I use AI in the same way that I'd use a rubber duck, but a rubber duck with the power of memory. I explain what I think the code does, ask it to challenge that understanding, and then incrementally build on my mental model. I keep the scope tight by pasting only the smallest relevant snippet, because zooming in only works when the problem space stays constrained. Whatever AI gives me back, I then treat as a hypothesis to validate, not as the final answer, because AI and we have a little bit of trust issues. Finally, I use tests as validation. When I think I understand how something works, I try to encode that understanding in a test. That might mean extending an existing test or creating a new one that captures my assumption. If the test behaves the way that I expect, it means that I've got my mental model correct. If it doesn't, that mismatch is also valuable, telling me where my assumptions are incorrect. Zooming in like this gives you momentum, a way to make progress without feeling overwhelmed. Once you've gained traction in one small area, the rest of the system starts to feel more approachable because you've already found a foothold. It's that foothold that allows you to step back, zoom out, and start reasoning about the system at a higher level, not as an abstract whole, but as something that you've touched and tested already. After zooming in on one concrete behavior, I then zoom out, not to understand everything, but to sanity check what I've learned and to decide what to do next. When I zoom out, I'm running a small set of deliberate checks to understand what kind of system I'm dealing with. The first thing I do is I look for structure. I'm deliberately not tracing edge cases or execution paths. I'm trying to see the dominant shapes that the rest of the system orbits around. At this stage, it could be useful to reach for diagrams, something like a C4-style diagram to reason across different levels of abstraction. A C4 diagram will document the context, the containers, the components, and the code views. When I'm zooming out, I'm usually operating at two levels. It's the system's context as well as the major containers. To understand the context, I ask questions like, who uses the system and what does it depend on? To understand the containers, I ask, what are the big moving parts? How do they talk to each other? And where are those system boundaries? The component and code level views belong to zooming in once I actually need that level of detail. Next, I look for repetition. A clean code base repeats its patterns. It usually has a handful of ways of doing things, and it does it consistently. I'm looking to see if the system has reliable defaults. I start by comparing parallel areas of the code base. I'll skim 2 or 3 features or services that I expect to be similar and look for shared vocabulary and structure. I look for repeated journeys rather than individual files. I'll pick a common flow, like creating or updating a record, and trace how it shows up in different contexts. Where does validation happen? Where do state transitions live? Where do background jobs get enqueued? In a consistent system, these shapes tend to appear in familiar places. This is where editor tooling helps. At this zoom level, I'm no longer using an editor to trace execution or flow. Instead, I'm searching horizontally instead of vertically, scanning for the same naming convention, lifecycle hooks, state transitions, or abstractions that appear across the code base. When the same shapes keep showing up, that repetition becomes evident. Then I look at how the system changes over time. I'm running a few quick checks to see where work tends to accumulate. I skim recent change history to see which folders or components keep showing up again and again. Where do new features usually land? Where do fixes cluster? Do the same areas keep absorbing the same new behavior? Do the same areas keep absorbing new behaviors? A directory that's touched every week tells a very different story from one that hasn't moved in years. If every feature seems to punch through the same layer, that layer is probably doing a lot more work than it actually should be. I also pay attention to how changes happen. Are most changes additive, extending existing flows? Or are they invasive, cutting across multiple layers? Repeated invasive changes are a signal that an abstraction might be under strain. I'll often use AI deliberately. I'm asking it to summarize patterns over time, condense Git history for an area of the code base, and surface recurring themes in pull requests and in discussions. At this level, boundaries aren't just technical. They're human. Components will often change together because they're owned by the same team. Some areas interact with stricter interface by design because multiple teams own that, and so the responsibilities are split across these teams, and hence we want to make them stricter. Noticing these details can explain why the architecture looks the way it does, and it also tells me who I need to speak to if I want to make changes. Zooming out like this doesn't give me a complete or authoritative model of the system. What it gives me is confidence that my understanding is directionally correct, enough to move to the next step where those shapes will turn into explicit patterns that I can reason about deliberately. Knowing when to stop is just as important. At this point, enough means that I can trace to explain through the system's main flows in plain language, I can name the key components, and I can point to where important state lives. That's enough to work deliberately, to make changes, to make assumptions, anticipate side effects, and know where I need to verify. That is the signal to stop zooming out. Once I have a rough but reliable pattern, once I have a rough but reliable mental model, then patterns start to emerge naturally. We almost never start from zero. Even in an unfamiliar code base, familiar shapes always appear in the language, in the architecture, in the API, and even in the data models. Recognizing those shapes early on will help you to decide which questions to ask next. And when a system doesn't fit a known pattern, that's often the most interesting signal because it reflects a real constraint or a historical decision that we should try to understand more about. I'll walk through a small representative patterns that I use to orient myself in a real code base. We'll start off by talking about Ruby, then we'll talk about the architecture, the API, and finally the data model patterns. So let's start off with Ruby. Ruby code tends to use certain constructs in very predictable ways, and recognizing those patterns early on will help me to orient the code base much more quickly. I'll show a few concrete examples of how I use these predictable constructs to guide the questions that I ask to navigate a Ruby code base. So when I see blocks being passed around, especially at a class level, I assume that it is being registered or configured for later. So this leads me to ask questions like, when is this class block executed? In this example, who calls the get method? And what context does the method run in? Include, extend, and prepend are strong signals of how behavior is composed. In this example code on the left, I'll ask questions like, where does the audit method come from when it's called? Is this adding instant or class behavior? And is anything being wrapped or overridden? When method missing appears, and in the Rails source code, method missing appears many times, the system is usually presenting a dynamic interface in that case. The important questions here aren't really about the implementation details, but when you see method missing, you think more about scope and safety. Which method names are valid? What are the set of method names that are defined? And how does this affect debugging and tooling? When methods are generated dynamically using, for example, define method like in this code snippet, it means that the behavior is often derived from data or configuration. So rather than trying to first understand the code itself, you look for the source of truth, trying to understand where does that name for that dynamic method come from. In this example, when is the model class defined and what input controls the surface area of this API? Seeing send or public send is a clear signal that behavior is being selected at runtime. From this example on the left, I'd ask questions like, where does the email method come from? Is it trusted? And what are the valid options for this method? When core classes are reopened, the ground rules of the system change, and this changes assumptions globally. When this happens, I want to know, where is this loaded? Who relies on it, and what breaks if it's removed? Across all these examples, recognizing this pattern means that I formed a hypothesis. Ruby makes it very easy to express intent tersely, but it also makes it very easy to hide complexity. So every pattern that I recognize comes with a follow-up step, validation. Find the call site, trace the data, and check the tests. Once I've oriented myself at this level, I can then go full circle and zoom back in with intent, knowing which details matter now and which ones can wait. When I talk about architecture patterns, I'm actually talking about different signals at different levels of abstraction. Some patterns will describe the overall shape of the system, how it's split and how it's deployed, while others describe how behavior flows through the system. I don't try to reason about all of these levels at once. Instead, I move down the stack, letting each level narrow the questions that I ask. For example, the first thing that I try to understand is the overall shape of the system. Am I in a monolith, or am I dealing with a system of services? This is the navigation queue that determines where the boundaries live and how the consequences propagate. In a monolith, boundaries are often conceptual rather than physical. Everything may deploy together and possibly share a database, but that doesn't mean that the system is one uniform blob. The useful questions become, where are the internal seams? how are responsibilities grouped, and what internal interface does the code base rely on. I look for directory structure, naming conventions, domain boundaries, and places where the code tries to enforce separation. When something breaks, debugging usually means tracing behavior through shared code and shared data. In a microservice architecture, the schemes are more explicit and enforced. Each service has a boundary, usually indicating separate deploys, separate ownership, and potentially separate data. The questions shift immediately. Which service owns this concept? Where do handoffs occur? And is that integration synchronous or is it asynchronous? Debugging becomes distributed, and it's more important to, it's often the first priority to understand where the boundary is rather than the code in the service. One level down, I'll start looking at how behavior moves through the system. Is it request-driven or is it event-driven? Once I know which of these worlds I am in, I start asking questions further down the stack. In a request-driven system, the critical path is usually synchronous. So a request comes in, the code runs, and then the response goes out. That immediately tells me where to start looking in the routes, in the controllers, service boundaries, and points where the request hands off to persistence. The questions are concrete. Where is validation and authorization enforced? What must succeed in order for the user to get a correct response? And what happens when something in that path fails? In an event-driven system, however, the center of gravity completely shifts. The unit of behavior is no longer the request. Instead, it's the event. Instead of starting at roots, I start with the event definitions. So what event exists and what are their schemas? Who are the publishers and where are the consumers? What guarantees exist around durability, ordering, and failure? Those questions lead me to completely different artifacts: event catalogs, broker configurations, retry policies, subscriber registries, and item potency guarantees. Most real systems, however, are hybrids. So a user action might be synchronous up to a certain point, but then it will fan out asynchronously into jobs or events. Recognizing that early stops me from chasing the wrong thread. If a behavior seems missing in a request path, it's often because it happens later somewhere else. Finally, I pay attention to which boundaries mirror teams. Architecture diagrams show boxes and arrows, but in practice, boundaries often reveal themselves through ownership. Which components change together and which ones deploy together, where handoffs happen and where friction accumulates. Those human boundaries often explain the technical ones. They tell me who needs to be involved before I make changes. The goal of recognizing these architecture patterns is to guide where I look, what I trust, and which questions I ask first. Once I understand the language level and the architecture level shapes, I then move on to API patterns next. APIs are where the systems make promises. They define what the system exposes and what it considers to be stable. Recognizing those API styles changes assumptions about correctness, ownership, and failure. One of the first signals I look for is the organizing principle of that API. Is the system primarily resource-oriented? Is it schema-driven? Or perhaps is it operation-driven? Each of those shapes push me towards different starting points and different questions. Ooh, what did I do? In a REST-shaped system, the organizing principle is resources. I expect behavior here to be grouped by nouns rather than actions. This immediately tells me where to start: the root table and the controllers, or the handlers associated specifically with that resource. From there, I'll go on to ask practical questions, like what is the canonical representation of this resource? Where are invariants enforced? Is it in the controller, the service, the model? How are authorization and validation applied? As mentioned earlier, with a request-driven REST API, you can often follow the request path from end to end because that contract usually lives in a synchronous flow. In a GraphQL system, however, the contract lives in the schema, not in the roots. So when I recognize the shape, I stop looking for endpoints and instead look for types and entry points. I ask questions like, which types represent the core concepts? Where do fields fan out into deeper dependencies? And how is responsibility divided across the resolvers? The questions here aren't, which endpoint is this? But instead, it's which fields are responsible for this behavior. The schema becomes the map, and the resolvers are the terrain underneath. In an RPC style system, sorry, my thing seems to be very trigger friendly. In an RPC style system, the organizing principle is operations rather than resources. When I recognize this shape, I stop looking for a canonical model and I start looking for surface areas of actions that the system exposes. I begin with the service or method definitions and I ask, what are the stable operations, what does each one promise, and how are breaking changes handled? I also look for the system's expectations around retries and idempotency, because RPC systems often operate in environments where failure is assumed rather than exceptional. All of these questions lead me to artifacts that matter: service definitions, message shapes, version, migration, and compatibility strategies. Together, they reveal how changes happen at the boundaries, which APIs are fluid and which are stable, and where the evolution is constrained. I look for cross-cutting signals that reveal the system's true constraints. Pagination and filtering often hint at data volume, query shapes, and performance trade-offs. Idempotency tells me where the clients are expected to retry and how the system behaves under duplicate requests. Rate limiting often reveals what the system is trying to protect and which workflows it considers the most risky. Error shapes reveal that whether failures are treated as part of the system or whether they are treated as incidental details. These signals are pretty small, but they carry a lot of information about how the system is meant to be used. Finally, looking for the API contract then helps me to validate my understanding. So I look for a formal specification or a schema, and I treat it as a map to verify my understanding against. If I don't find that, I rely on integration tests as well as client usage as a source of truth. And failing that, it's the implementation itself. When I recognize API patterns, I can then orient myself. It helps me to determine where to start reading, which assumptions are safe to make, and what questions will get me to the truth fastest. So once I've understood now the language, the architecture, and the API, I turn to the data model. Data models, in my opinion, are the most honest part of the system. Code can be refactored, APIs can be reshaped, but data often preserves its intent. It's a map. It tells me what the system truly cares about and often where its real boundaries are. I don't approach the data model to understand every table or field. Instead, what I'm looking for are core entities that exist to support or extend them. A useful early question is, if the system disappeared tomorrow, which records would matter the most? These usually point to the primary concepts that the rest of the system orbits around. Ownership is usually a good signal. In some systems, there's a clear primary record that owns most of this behavior, and then there's other tables that fan out from it. Relationships are directional and intentional. When I see this, I look for state transitions that are driven by that primary record, and for side effects like background jobs, notifications, and downstream updates that are initiated from that lifecycle. My questions focus on invariants, like what must always be true about this record, and where are guarantees enforced. In other systems, ownership can be more diffuse. Multiple entities will evolve together, or the same concept can appear in several shapes across the system: raw events, derived views, aggregates, and caches. When I see this, I stop expecting a single source of truth in one table. Instead, I ask, How is consistency managed, and what representation is authoritative in which context? And how long does it take for the system to converge? Because time here often becomes part of the data model. I'll also pay attention to how relationships are expressed. Polymorphic associations, soft deletes, join tables, and denormalized fields are all signals of trade-offs. A heavily normalized system often prioritizes data redundancy, integrity, and storage. A denormalized one, however, often prioritizes simplified queries and read performance. They each have their use cases, and each one will guide how I reason about queries, updates, and failure modes. Another useful signal is history and how it's represented. Some systems will override data pretty aggressively, only keeping the latest version. Others preserve history through audit tables, append-only records, or event logs. When I see history preserved, I know that past state matters, either for debugging, compliance, analytics, or replays. This impacts the consideration that I give the data when modifying my writes or when performing migrations. Lastly, I look for where the data model will connect with the rest of the system. Which fields show up in the API? Which ones drive permissions, workflows, or background jobs? Data that crosses many boundaries is usually a little bit more sensitive than data that stays local. Understanding that early helps me to avoid creating small changes in the database that then ripple outwards in unexpected ways. At Circle, we tend to use tools like the Claude MCP, which is really useful. When you ask it the right questions, it can then summarize the data models, or it can help you to explore real production data to see how those tables and relationships connect in the real system. That's especially helpful for validating your assumptions, not just what the schema says, but also how the system behaves in practice. The goal here is to form a hypothesis about what the system values and what it protects and what it optimizes for. Once I have that, I can navigate the code base with more confidence because I'm no longer guessing what matters and what's important. So by this point, I usually have a solid understanding of the system. I've zoomed in on specific behavior. I've then zoomed out to see the architectural shape. I can potentially then zoom in into a different area, and then I recognize patterns in the language, the API, and the architecture, and the data model. I've built a good mental map that allows me to navigate with intent, but there's still a gap. I know how the system works, but not why it ended up this way. That's where context comes in. Code captures decisions, but it does not capture the context behind those decisions. Without this context, it's really easy to misread intent, to assume that something is accidental when it's actually defensive, or to see complexity and assume that it was avoidable. At this point, reading more code stops helping. Instead, I look for signals of history. Git history shows me which parts of the system change frequently and which have remained stable. Pull requests, commit messages, and documents will hint at things like urgency and uncertainty and compromise that occurred. It shows us what the system was trying to be, even when in reality this diverged. I'll often use AI here to help me to summarize threads, Slack discussions, or incident write-ups so that I can spot recurring themes and inflection points more quickly. It's useful for compressing context over time, but it can't tell you which decisions were political, painful, or risky. For that, you'll always need people. And this is where conversation matters, and how you approach that conversation matters just as much. I'm very careful to remove judgment early and lead with curiosity, because most decisions actually make sense once you try to understand them. So instead of forming an opinion prematurely that something is really bad, I start by asking questions that surface that context. What were the constraints that occurred, and what was the problem that we were trying to solve at that time? That mindset really matters because systems are never a result of just a single clean design. They're the accumulation of many, many reasonable decisions made under pressure. We all know there's deadlines, incidents, partial information, and shifting priority, which all leave traces in the code base. When you treat the system as an outcome of trade-offs rather than mistakes, people within the team are more willing to help you out and share missing context that doesn't appear in the repository. Understanding context is ultimately about respect. Respect for the system and respect for the people who've worked on the system. When you combine structural understanding with historical context as well as social context, you start treating that system as a living thing. And that's what allows you to make changes to improve the system without breaking the trust around it. Oh, sorry. By the time I reach this point, I've done a lot of work that exists only in my head. I've built mental models, I've uncovered patterns, I've learned history, and I've understood trade-offs that aren't obvious from the code alone. That understanding is valuable, but it's also really, really fragile. If I don't externalize it, it disappears. If I don't preserve it, the next person needs to then rediscover all that from scratch. This is where understanding either compounds or evaporates. You can externalize understanding by leaving traces about what you've learned. Some forms of this may be writing down the shape of the system as you now understand it, capturing the assumptions, and capturing the constraints. You can also create lightweight artifacts like an architecture.md that people can read from, that AI can read from as well. A simplified diagram or even the more detailed diagram like the C4 style one that we discussed earlier. And finally, you can always improve on the test to describe how the system is expected to behave at those boundaries. There's a strong relationship between zooming out and preservation. When you zoom out, you often surface things that live as common knowledge within a team, things that we assume everyone knows but has not been written down. Externalizing that knowledge turns it into a system of record. It gives you something to point back to when the system evolves and decisions need to be made revisited. A concrete artifact that you can use now to onboard someone new, or to align with a different team, or even to communicate technical boundaries to external stakeholders who may interact with the interface of your system, but not be within the code of your system every day. This is also where the repeating patterns that I talked about earlier start to matter beyond that moment. When you notice the same shapes appearing over and over and over again in how services are structured or how the API evolves or even how state transitions are handled, these patterns are then candidates for shared guidance, not rigid rules, but guidance on how we approach certain practices. Over time, this can be a form of written best practices grounded in the reality of the system itself and not in some sort of abstract ideal. AI changes the stakes here. You're no longer just documenting for the next human, but you're also documenting for the next agent. I mean, with AI tools being able to read, reference, and reuse architecture notes, data models, and diagrams from your repo, it makes it pretty valuable to have some of that documentation there. If you had to explain a constraint, a boundary, or a historical decision to both a human or an agent repeatedly, then that means it should probably live somewhere more durable. And that's how understanding compounds instead of resetting with every new task. Of course, I've gotten this question so many times over my career, but everyone raises a point at some point, like how do we keep this documentation up to date? And honestly, there isn't a perfect answer. But in my experience, documentation stays current when it's treated as part of the system and not an afterthought, when it lives close to the code, when it's updated alongside code changes, and when it focuses on explaining the why rather than the how. It tends to age far better than exhaustive references that try to capture every single thing. So externalizing understanding isn't about completeness, it's really about leverage. A small amount of well-placed context can save you hours of future exploration. It can help to prevent repeated mistakes and make the system easier to reason about for you, for your teammates, and increasingly for the tools that help us to build. So in conclusion, you'd zoom in to learn, you'd zoom out to see patterns. You can then zoom in again to learn more. You understand the context that shaped the system, and then you externalize that understanding to let it compound. Ultimately, you want to leave the system in a better state than you found it, but not just in code, also in clarity. And that's how I've learned to build understanding in complex systems. Thank you so much for listening to my talk. My name is Ridhwana, and you can find me on Twitter or LinkedIn, and I'd absolutely love it if you come say hi.